Great. Okay. So yeah, as I said, there are many postdocs are traveling already. So somehow this week we have a lower occupancy. That's fine. Okay. Today we're really happy to have Rodolfo Capdevilla. That pronounce your last name reasonably well. Yeah, I never tried, but this is my first time. From Fermilab to give us a talk on road to minimal WIMPs. Let me briefly introduce Rodolfo. He got his PhD from Notre Dame, working with Adam Martin. Then did his first postdoc at University of Toronto, and now he's finishing up his second postdoc at the Fermilab. Rodolfo has been working on a lot about DSM physics at colliders. In particular, recently in muon colliders, but he also explores many other physics opportunities, including some cavity sensing, gravity waves, etc. If you are interested in those topics, feel free to find Rodolfo and chat with him. He'll be here today and tomorrow as well. When are you leaving tomorrow?
Tomorrow Saturday.
Yeah. So feel free to approach him and discuss physics with him. Okay. Without further ado, please go ahead.
Nice. Thanks so much for the nice intro. Yes. Hello everyone. I'm gonna be telling you about these minimal WIMP models. I'm gonna define them in a second. This is work with my collaborators here. Oh wait, I should. No, wait. What am I doing?
So that's how much trouble we have got.
Yeah. So I can just okay, good. Yes, so I'm gonna have a brief intro where I define this. What do I mean by these minimal WIMP models? And then I'm gonna tell you how different experiments explore these models. The prospects for future colliders over here, including proton electron colliders and the muon colliders. And what we're going to be doing is a roadmap from current to future experiments, how we're going to be covering the primary space of these models, right? So what I mean by minimal WIMPs, so maybe some of you know in the literature, there's the name minimal dark matter, electroweak interacting dark matter, minimal WIMPs. The idea is that you introduce a new particle that is a multiplet of SU2, a doublet, a triplet, or something beyond, and you choose your hypercharge so that there is a neutral component in the multiplet, and that neutral component plays a role of dark matter. Yeah, there are more details that I'm gonna tell you.
Skip 7.
What's that?
Why did you skip 7?
I don't know. But yes, so these models, they are so highly motivated. You can see them as part, like doublets and triplets in a supersymmetric construction, like the Higgsino particles around the TVA scale. Or you could play the simplified models game, and then so you got your doublet triplets around this scale, and then higher multiplets at a higher scale.
Okay, why did you skip 7 bullets? What are there any reason?
I don't know.
For 2 slides.
I hate them. No reason really. Maybe.
Why do you say that they're why do you say that they're highly motivated? The only one that's highly motivated would be Susie coming.
Yeah, I mean, this depends on how we define highly motivated. There's also motivations if you look at the simplified model version where you just in the sense that it's minimalistic. It's a minimal setup. Just introduce
motivation setup. What other problems does it solve?
No, just dark matter.
Well, then why is it highly motivated? You said it was highly motivated.
Well, depends on what do we define by highly, right?
Well, it has to satisfy solve a lot of problems. Right?
Yeah. Okay, so I'm defining highly as if it solves dark matter, it's highly motivated.
So highly motivated means you solve one problem. That's what.
At this point, if we find new physics anywhere, they'll be highly motivated.
Why you're looking at these particular representations?
I think if you go to the higher representations, then they are more stable, right? Yes, like kind of more stable against like a Born correction coming from Born gravity or something like higher image operator. So in terms of the lifetime, so it is still just like an explanation of the rock model, but in terms of the lifetime, like, they're good. They have some good features.
Yeah, that's what I was trying to figure out, like. is
Yeah,
there
yeah.
Anything else?
No,
besides
no,
the matter that they
I guess I just put the examples of, but I'm not like advocating for these two particular hypotheses. Just saying there are also just larger multiplets.
But
Yeah.
is there any motivation to study the larger multiplets except just to write another paper? That's my question.
I see. So let me see.
I mean, like what Yohei is saying, maybe they're more stable. That would be an answer, right? But is that true? I mean, there's other motivation for studying these other representations or not?
Let me
That
see.
you're aware of?
So that I aware of, no, it's just the fact that it's a minimal extension that gives you that matter quite naturally, in the sense that what you impose is that you want the neutral component to be the lightest. And then, yeah.
So when I work on this topic, I gave a slightly different viewpoint. I would say the minimal dark matter is interesting strawman to represent not only a minimal setup for a dark matter, you can choose different representation, but also the hardest to test the setup. Okay? So other dark matter kind of co-annihilation or other processes are more visible signatures. For those higher representation of minimal or higher representations of minimal dark matter, they are highly degenerate state, not observable, and high thermal target. So basically, that's a very hard to test WIMP scenario. If you are able to cover that, you will be able to cover essentially any other WIMP models that are massive.
Oh, so your approach is like, this is a nightmare scenario.
Yeah, this is
And
they call it minimal scenario because it's only requiring introducing one multiplet. That's simple. But on the other hand, there's no strong motivation to go to higher representation. But except for that, they are the hardest to test scenarios. So if I assume you're going to talk about muon collider covers this, they will be able to cover that.
But
no,
again,
but
there's never a bigger picture to incorporate these other multiplets.
Yeah, there's no bigger picture. In fact, the higher multiplet one, RG running is really fast. The higher component.
That's true.
Yeah, so it's actually
worse.
Yeah, the unitarity breaking scale is actually closer.
So then it's demotivated.
From that point.
Yeah. I guess we're gonna agree on this. So when you compute the annihilation in the universe, you find things like this. So the cross-sectional annihilation goes with how large your representation is. So the larger the representation, the more you deplete this dark matter in the universe. When you have little dark matter, you need it to be heavy in order to accommodate what we know about the thermal the relative density. This is when we call it the thermal target is the mass that you will need for a given multiplet to give you that amount, the full amount of dark matter. So you can see for doublets, you need 1.1 TeV masses, triplets, 2.7, fiveplets, and so on. And then, they become less motivated because at this point, so beyond 7plets, you start developing Landau poles that scale very close to the mass of the particle, right? So then they become very not motivated. So a good point. Yes. So there's another feature of the model that's gonna come when we discuss this roadmap that I'm telling you. And the feature is that in the minimal scenario, you have so the mass of the multiplet will be the mass of the charge or the neutral component, but then the charge component gets some self-energy corrections that give you a small splitting. It's a loop effect, and it's a small correction. So then you should think of the spectrum as something like this by construction, because we want the lightest to be the matter. Right? So then, but in here, something secretly happened is that you need this state to be Majorana in order to evade direct detection constraints. So think about how in supersymmetry the neutralinos they mix, and so in principle this spectrum could move around and approach MK depending on. Right, this could be very complicated, right? What's happening there? Like in supersymmetry is the mix of the neutralinos, But in the simplified model version, it could be, for example, you introduce higher dimensional operators that then give you this extra mixing or things like that. Right? Okay, so then this splitting gives you a macroscopic decay length for the charged particle. You think about this is PV masses and splittings that are the order of 0.3, 0.35 or something like that in GeV. And you get things like 10 millimeters in decay length. This is the example of the doublet or Higgsino case. Yeah. So then by roadmap, what I mean is this. So there is a minimal setup that will give you a thermal mass, as I told you before, and that will correspond to some splitting that will give you a particular lifetime, right? So as you decrease the splitting, what are you doing? You are increasing the lifetime, but then you enhance co-annihilations in the universe. You deplete more dark matter. So as you move in this direction, you're going to need a heavier mass in order to keep accounting for full dark matter density. Yeah. So the contour moves more or less like this. This is very rough because this is going to depend on the particular multiplet that you add. So just gives you, I'm just giving you a cartoon. Then as you move in this direction, you're going to be your multiplet accounts for less and less of the dark matter. And the roadmap is basically saying, oh, we're going to go covering this parameter space all the way to the thermal target.
Is this a real calculation or just a cartoon as well?
It is a cartoon because it depends on the multiplet, but we're working on the different multiplets and.
Yeah, so is this correspond to a particular representation or you just randomly draw a curve and
Like the triplet looks.
so it is actually a triplet.
It's a schematics of the triplet case. Yeah, I'll be more precise later. So like in searches, right? So you get the dark matter direct detection experiments. Here I'm showing you the neutrino floor, right? So then look at all these, the cross section for all these multiplets. They fall within the projections of this experiment. And then, well, sadly, for the 2 and the 5, they are below the neutrino floor. So, but
where's the neutrino floor?
It's in the pink, this pink line over here. Yes. So this is about 2 orders of magnitude below, and this is.
And the left end, what's the energy? What's the mass on the left end of the axis?
Over here.
Yeah.
I'm not sure. This is the 1.1 doublet fermion Majorana case. But yeah, I'm not sure how far it goes. Are you thinking about?
Because I don't know where I never look into the neutrino floor in the high dark matter mass region. I typically was talking about the lower dark matter mass regions, the solar neutrinos and others. I didn't expect the neutrino floor to behave like this.
I see.
Seems that there are more background. Or just rate.
Yeah,
it's the same rate I cannot distinguish.
Yeah, here I think number this is as one minus.
Maybe this corresponds to constant event rate of the neutrino background, and you don't know how to interpret it. So you as a flux for your dark matter.
Yeah, this is the paper about diary on the Earth.
So the doublet Fermi on there, that's like the Higgsino.
Mm-hmm.
And it's below the neutrino.
Yeah.
And then the triplet.
It's a little above.
The triplet fermion, that's like the neutralino, and then you're taking the same couplings as in the Susie model, G2. Or are you varying?
Yeah, it'll be
Like
like the Wino, yeah, the triplet. Mm-hmm. Yeah.
So you're taking the same couplings,
Yeah, it's electroweak coupling, yes. Yeah.
So how precise is this for you can't go stage. Case on complex, triplet, like within 1 or much, but so much.
Well, they make an estimate of error bars here. I guess what you're asking is the error bars in here, right? Yeah, I wouldn't know. I would refer you to this paper to see and to see more details. But yeah, we can discuss it. So projections look good, at least for triplet case, 4, 6, doublets, fiveplets, for outside of the projection. And then indirect detection, right? You could find for very energetic gammas from coming from space, because these particles are dark matter and they annihilate. This is very recent from these authors. You see, for example, this is NSW profile. This refers to the dark matter density profile in the galaxy, right? And this gives you at most 2 sigma from this is CTA Cherenkov-Telekov array. So the projections say you get at most 2 sigma if you use this particular assumption. But then different assumptions will give you different results. So at the very least, we can say this is non-conclusive, but it could give us evidence of this particle being dark matter.
Is this projection or interpretation? Are they reinterpreting CPA data based upon different profiles?
As I understand, it was projection, because like yes. Oh, and then something that's been known since a few years now is that for the triplet, the Wino-like, you have the annihilation cross section is well above what the projections, the sensitivity tell you. So this is said that is ruled out as that matter. Yeah, the triplet. But then where these 2 direct detection, indirect detection searches shine is in this point where the particular the Higgsino gives you the full amount of dark matter of the universe, right? So then, as you can see, this is covered by the searches. But then, as you relax that assumption and you say, let's imagine that axions give you an important fraction of dark matter, or 50-50 or something like that. So if you are at 20-30% of dark matter, you are still in the 1.5 TeV range. And you escape those constraints, right?
If then you need something else for the dark.
Exactly, you will need some axiom, something else.
Just do it with the axiom, throw it away.
So you're saying that if we find a triplet that gives you 20% of dark matter, wouldn't be happy? I think we will be very happy.
You can say you need an axiom. Now you need the axion is not 100%, the Wino is not 100%, and magically the axion and the Wino together give you 100%. That's what you're saying. Right? That's what we have to have.
No. I'm just saying, I don't know about anything else. I'm just saying, if this gives you 20% of dark matter in the universe, I don't know anything else. That still be highly motivated, wouldn't it?
That would be one.
Highly motivated, right? So a triplet state giving you 20% of dark matter of the universe.
Why is that highly motivated? It must be used with your word, highly motivated. It's too optimistic. Maybe there's another word.
Okay. Okay.
But like indirect detection, like it depends on, of course, like the profile of the data.
Yes.
Maybe you mentioned.
No, for the doublet, I know it's a big deal, but for the triplet, I think the bound is so far below that.
So this bound is computed by using like this not a peak profile, but also molecule.
Yeah. I think this is somewhere here. I think this is different assumptions. But then, as you can see, these are very old papers. The thing is that I ask around these people, and there's no more recent version of this plot yet. But yeah, like all these assumptions, they already cover an important fraction here of this.
People also try like a co-op type profile.
As I understand, yes. Dan mentioned something like that.
Yeah, the orange line, that's a pure minimal, like a pure Wino case, right?
Mhm.
So your 2.9 TeV benchmark. There's only one limit, one constant, that is the XESS line. Right?
Has
the band, I have to assume they've iterated around different profile asperities to derive that. Otherwise, how do they take into account the profile?
Yeah.
So we can only know what profile variability they assume by looking into that data. But that in principle, there's only one big
Mhm.
from this plot. The
Yeah.
previous plot, can I go back?
Yeah.
Seem to be a projection.
In this one?
Yeah. I've seen this plot, but I never digest that.
Yeah.
Yeah, is it a projection? Is it a real limit?
Okay, I owe you that info because I thought it was a real lead, but maybe it's a projection. Yeah.
Yeah,
But
it's
yeah.
drawing this yellow, green color, make you feel it's a limit, right? Maybe.
I see. Yeah. Okay, so then in a sense, direct detection and detection, they shine in this region, right? So they will be covering this from right to left. But again, it's model dependent, right? That's why I'm being rough here, because the doublet wouldn't for direct detection wouldn't cover any of this. Yeah. So now our dear or my dear LXC. So as I told you, the different assumptions could be going on here that could push this spectrum so that you reduce this gap. So then you enhance the lifetime of chi plus. Yeah. If that happens, you can apply these heavy stable charge particle searches, and stable means above 50 nanoseconds, and they are very good. Look at this. So this is Chargino. At this particular search, they are assuming some particular SUSY spectrum. Yeah, but like the bottom line is that they go up to TeV scale. That's good. They use things like the amount of ionization as the particle passes through, the time of flight. Those are very good variables to discriminate. And yeah, so you want to know more? Here's the paper, and so this is coming from this corner over here and below, and then disappearing track, because this particle is going to have I told you a macroscopic lifetime, but then maybe that lifetime is not long enough so that this particle disappears in the middle of the tracker. That's a very good signal that they can catch. And as you can see, they cover a primary space like this of a few hundreds. This line over here will give you the lifetime of a triplet minimal dark matter case. Right? So about 450 or less. So this is covering this region like this. It doesn't reach as high masses as this search, but it reaches lower lifetimes, for example. And then you can do things like vector Boson scattering or electroweak precision test. This is just an example, but this also gives you bounds on the mass depending on the multiplet you have. But as you can see, they are quite weak. But this type of constraints, they are coming from this way. Right?
So what was J?
This is also the size of the multiplet would be 2JF plus 1. So this is a 5-plet.
Spin.
Yeah, spin.
The total spin.
Yeah. So then, yeah. So.
Yeah.
Right. So then, very roughly speaking, the LXC is coming from this side. These experiments are coming from here, and there is a middle ground where future colliders they cover, right? But that's the task for them. So look at
Go back that Capdevilla plot.
yeah.
So what is not covered, right? Is your target the blue line?
Yeah, the target is the permanent, yeah.
The things are excluded are to the.
It'll be LXC will be like this.
Yeah. And direct detection?
It's coming like this.
As you're telling me, direct detection already fully excluded your dark matter.
But again, it's model dependent because the doublet, right? So for the triplet, this is not there, but indirect detection, you could say there's there. But even if those experiments find a conclusive signal, you still want to get there. You still want to be able to produce this particle in the lab, and
Oh, for the
I-
discover, I will do my lab. If they could, I may not do my lab.
yeah.
So you're saying that there could be a solid line in the gap there of future collider? Can there be a solid line where you get all of the relic abundance?
Yes, for the doublet, that's how it looks. For the doublet, this line should not be there. And LXC can do certain amount, but still the thermal target will be a task for future colliders. Yeah. Yeah, and I show you, that's precisely what I'm going to show you here. So we have electroweak states above the TeV scale, clearly a task for future colliders. The LEC has a hard time producing these states, or at least detecting them. So we're gonna talk about the proton collider at 100 TeV, click with an energy, it's an electron collider with an energy at most of 3 TeV, and the new kid in town, the muon collider, with energies of 3 and 10 TeV. Yeah. So back around the time where people were excited about the 100 TeV collider in China, so Liang Tao, Matt, they put out this paper showing how the Wino, the triplet state, could be covered at around 5 sigma within uncertainties, all the way up to the thermal target, as you can see. It was a very exciting result. They pointed out that the doublet was very tricky, but then there were some further work by these people or the authors claiming that indeed that machine could also get to the thermal target of the doublet. Yeah. As you can see here, between 20 and 100 events, somewhere around that. And then, for the developments about the triplet, nailing it down better and better.
Let's go back. I saw the Wino already in the previous project already covered.
Yeah. More or less, yeah.
Yeah, so the next slide, they just,
They're just like reducing uncertainty. Yeah.
it's a discovery.
Mhm.
So on the left panel, what did they do?
This is the doublet.
Yes, the doublet case is challenging. What did they do?
This is they're looking for disappearing tracks. Yes, disappearing tracks, as I understand. And just you're talking about why this one is different from this one, you mean?
Oh, I know. It must be looking for something beyond the emitting energy. So, what did they do?
I understand it's disappearing track, but as I understood this one, this was also disappearing track. So I actually don't know what changes from here to here. That's a good point. I should look at in the yeah.
No,
It
no, the band is all emitting energy. I know exactly what they did in the previous.
in the previous one, yeah.
So I don't know what's the disappearing track.
Oh, disappearing tracker. What do you mean you don't know?
I thought they did the emitting energy search.
They did. They also did monojet, but it's worse. The reach is worse for monojet. And so this is the optimistic.
So you choose the better, but
Yeah.
the
Yeah.
spare track has been improved dramatically.
Exactly. This is what I'm trying to say here, that disappearing track has been improved a lot since within 3 years. But I don't know the details here, right? So yeah. I don't know the details of this.
It depends a lot. Okay, so for instance, this paper, if I recall correctly, if I would claim to cover that, they have to assume I put the first layer of tracker, within a few centimeters of the beam. So the currently the detector, the first layer of tracker is like 10 centimeters away from it. The lifetime of this Higgsino is 0.6 millimeter. Sorry, 6 millimeter. So it's really hard for it to travel to that to register the idea. So this one they have to assume FCCHH has a special inner tracker that to register those disappearing trackers. Is it possible? I don't know, but people doesn't stop people from making good assumptions.
Yeah. that sounds like similar discussion they have, these similar authors and David, but for the EP collider, where they discuss this, the proximity of the inner layer. Yeah, yeah, thank you. I'll look into that in more details.
So what's the difference between 1.1 and 2.7? One's a scalar, one's a Fermi?
No. This is the Higgsino-like. I should put the label, but this is the weak doublet.
That's the
Higgsino-like, and they are both fermions. And this is the like Wino-like. Yes.
Oh,
Yeah. Okay, so then click e plus minus 2 TeV. So you don't have enough energy to produce the triplets, right? So then the discussion here is about the doublet. Yeah, so this is the lifetime of the minimal case, and the thermal mass 1.1 TeV, right? And what you see in this line is the different stages of that project, where you increase the energy and luminosity, and then at the last stage, 3 TeV, 3 inverse atomic, you get to cover all the way to the thermal target. Right? So that sounds quite good. Okay, now to tell you all how the muon collider could now explore this primary space, I first need to tell you a little bit about this collider, like why.
So if click can do it, muon collider can do it as well. So is that the easy statement? The Higgsino doesn't care whether you are electron or muon. So if you claim 3 TeV click do it robustly, muon collider will be. Then what did the click people do? And why did you have to try so hard for the rest of the talk to this out?
Yeah, I'll tell you in a second. Yeah, let me just say just 2 words about, so the muon collider is that, so we like circular lepton colliders in the sense that circular because they are multipass. You in a sense, you recycle beam. They keep passing through each other. Then luminosity is good. You collect the data, and also power consumption is good. So we like that. And we like them to be when they are leptonic, because then all the center mass or energy is available to produce new states. So that's also something good. And that they are clean from hadronic background. So these are characteristics that we like from circular lepton colliders. But then the electron has a problem that at some point it radiates all the energy that you put in. So when you try to reach very high energies in a decently sized ring, the electron will radiate. So then the amount of radiation goes with the mass. So if you have a muon, then there is a lot less radiation. So you can in principle reach higher energies for a given amount of power consumption and yeah, parameters like that. So then with a ring of order 10 kilometers, you can reach 10 TeV muon collider. And compared to proton collider, this is 100 kilometers tunnel to reach the 100 TeV collisions, right? So these are the characteristics that then sort of like get people excited, and then the P5 report is saying this is our muon shot. Because so 20 years ago, people would say, no, 20 years ago, we also had the muon collider on the table, but didn't pay attention. Yeah, so 20 years ago, the muon collider was sort of in the same realm of energies as other lepton machines. People were talking about TeV, 1.5 TeV energies. So it was in a sense competing with click, something that's much better. The electron is stable. You can work with it much better. But now that we're talking about beyond that in energies that are, if you think about center of mass parton collisions, this machine is now competing or comparable to this machine. So the 100 TeV proton collider has partonic collisions of around 10 TeV. Right? So now it's different, and also the physics program of the muon collider has been developed a lot over the last 2 years. So then that's why the motivation is back. So I'm telling you, if you heard about the P5 and all, then you wonder why is this people making noise about muon collider. That's roughly the situation.
The first stage would be eventual goal would be to get to 10.
Yes. Yeah.
But same tunnel or it would be a different machine?
I think no, it's a different tunnel, but then I should put here the design. I think one booster becomes the ring of the other, or the ring of one becomes the booster of the other, something like that. There's one design like that. I should show you
But
that.
the idea would be it's one facility.
Exactly.
At Fermi.
Exactly.
None of the design is fixed. No, so far our cartoon drawings, so both from IMCC or US Real Collaboration, the design study there's no real layout. So
Yeah.
the plots I shows in my talk are the cartoon people draw on from that line. It's the US hope.
Yeah. Recently, this Senator Bill Foster came. He saw that picture and he said, "You guys are stupid. Like you should not put the boundaries in the current boundaries of Fermilab. We can go there. We can buy land."
Outside Fermi.
Yeah, apparently we can do that.
Fermi, that's surrounded by a house.
Or and like
Maybe to the east. I'm sorry, to the west.
yeah, he mentioned some big companies that are there and or like if you pay them whatever amount, they let you put a tunnel or whatever, you know, he said something like that. So yeah, in principle, yeah, Fermilab. So then back to Eugene's point, there are difficulties, of course, of the muon of the muon collider because the muon is unstable. So that experimentally gives you a lot of difficulties. For example, you want to cool the muon beam. Usually, when you prepare beams for collision, you cool them. So that means reducing the phase space. So now you can have a very focusing collisions. You can have luminosity, right, and things like that. So those are very far from me. So the difficulty related to the muon collider that is closer to me is that when the muon decays, then these particles, for example, especially the electrons, they're gonna collide with iron, tungsten, magnets and stuff. And all that's gonna propagate and then create all this noise in the detector. So this is called the BIP-induced background or BIP, yeah? So we need to understand this BIP and people have studied this. Okay, so the main components are photons and electrons, and as you can see, the spectrum it falls, and they are soft. Look, even below 1 GeV is the typical like at most the energies that they have, and then also is that they arrive late, right? So 0 means the bunch crossing in time, and then a little before and a little after that, you get the spread all these particles, photons, neutrons, electrons, and so on. Okay? Oh, those were the neutrons. Yeah. That's fine. So this is happening for bunch crossing in a window of about, this is just 100 nanoseconds, but you can see. Okay, yes. So what we need to, so people have studied this. As I told you before, this is back from the times of the MAP, the US Muon Corporation, 20 years ago. They did studies for a 1.5 TeV muon collider, so 750 muon beams. So now people have done new studies for the 3 TeV collider, for the 10 TeV collider, and so on. But back when we did this, our study, this was the BIP data available. Yeah. So then there's this pioneer work here, our friend. So looking at these very robust signals, where so the muon collider you produce the neutralinos, your dark matter candidates, and then you can have either 2 muons, 1 muon. This is a collinear photon from the initial or one of the beams, and then or one photon in the detector, right? So what they find for this is a very robust signals in the sense that you can have a very energetic photon, you can have very energetic muons and distinguish them from this noise background that I told you before. And look at what they find. So they tell us that doublets, triplets, the color is the energy of the collider that you need in order to conclusively, find this, or at least find the 2 sigma evidence of these particles. So look at the monomuon case for the triplet. You would need, between 14 and 30 3D collider to get it. But then for the doublet, with the monomuon signal, 610 3D collider would be enough. Okay? That's good. That's good. They go beyond and they tell us about the disappearing track. Same concept before, the Higgsino disappearing in the middle of the tracker. And look at these numbers. Now they look even better. The doublet, even the triplet now, for a collider around these energies, you will get that signal from 1 or 2 disappearing tracks. And then they went ahead and looked for all the multiplets. You can see that, right? So.
We didn't show my disappearing track, but projections the previous one. Underground.
Yeah.
Yeah, I just want to understand like in the meaning of this, so like 1 or 2D, like so in the previous slide.
Yeah, in the previous slide was just the monophoton and monomuon.
And monomuon is better than monophoton?
Yes. Yeah.
It's a unique channel here because the monophoton has actually have huge background. If you think about it, the monomuon actually for the background is much rarer. You basically require 4 muon to be not seen. So that's for my signal, I don't pay the rate suppression as the charge frequent multiplications of ion density. Yeah. So you come from charge neutral initial state, you seemingly have a charge non-zero final state. So that
Yeah, and here I'm just showing you that the 2 and 1 disappearing track, right? You usually require an extra photon in those searches. I'll tell you about that in a second, right? Oh, and then higher multiplets. Yeah.
So what's the difference between the Wino-like and then the Wino with hypercharge? What is that? Hypercharge.
Okay. So in this one, this is, so Shane can correct me, but this is the pure Majorana case, whereas in here, your particle is Dirac, but it has a little, it's like it's a millicharge under some hidden group. Yeah, some extra group.
Yeah, just to separate the Dirac versus the Majorana. This label.
Yeah. So this study then motivates these 2 questions, right? So then how can we go forward and see what happens with the full detector simulation, and also what happens with a more delicate treatment of the BIP? Yeah. So those were important questions to address. To draw a parallel, it's like in the 100-3 proton colliders studies. There's this voice in the back of your mind telling you, so how is Fermilab going to affect my analysis, right? And they go ahead and try to I study this the Fermilab. Fermilab refers to the per bunch crossing. You have many interactions happening at the same time, so the data piles up. So and here is similar. Is that the BIP is all this background, all this noise, and how can we address that? Can we really? Right. So that's what we did. So in the following slide, I'm going to be focusing on the disappearing track. Okay. The Higgsino is produced, and in the case halfway. So we needed to have a detector design, design. We just installed it from Click, and we put something called the nozzle here. It's a tungsten cone that shields a lot of this BIP-induced background. And the full experiment happens at what is called the vertex detector. Right? As you can see, is these 4 layers that are actually double layers of tracker, and they are within 100 millimeters of the interaction point. And that's where all the magic happens. Yeah, these are the nozzles I told you, and these are the different forward layers of the vertex and the transverse layers of the vertex. So this for those of you who are familiar with the language, so this is called the barrel region, and this is the end caps region. Okay, so I'm going to say those words later. And we exploited these properties that I told you about the BIP. That is very soft. So when you plot things like the PT, it falls very rapidly, the background, and your signal, it doesn't fall as fast. Yeah, so very soft. It arrives late. So as you can see, the beep is a spread of all this window of time, but your signal has a particular timing, right? So this is a light particle, but then when the particle is heavy, you can see how the particle takes some time between the interaction point to the detector volume that you are analyzing. And that time, yeah, so what in order to do this analysis, you need to choose a time window that depends on your mass. And then you kill all of the beam-induced background. And then the fact that it's mostly forward is that you study 2 consecutive tracking layers, and you see how your signal is coming from the interaction point. So the polar angle is small, whereas for the beam-induced background, the polar angle is very far because it's coming from the decay of the muons. So that's what I mean, mostly forward. So you exploit all those properties, and this is what you get. This is all the hits, and you get 3 orders of magnitude in background suppression. So now you can do what usually we do as theorists a lot. Is like, okay, so this signal is exotic, so 0 background. Let's start with that. Let's say this is 0 background. So as you can see, background, when you go from 1 disappearing track to 2, it's basically 0. The signal for the triplet, for the doublet, it's still hundreds of events. But this is happening in a particular volume of geometry here. So you need to be 40 degrees above in polar angle, and so forward and backward, right? So this is what you have here. Above the 40 degrees to 90, you get acceptances. This is the probability that you're gonna find your signal of order, you see 70, 80, 60, and so on. And these are the different layers of the vertex detector, right? So think about distance in this direction. This is what this is. So then if you see all this blue, that's going to answer Cheng's question in a second. Is that the reconstruction probability is 0 as you are very close to the interaction point, or if you are very in this far region, you lose the sensitivity. You need to be central in order to have good reconstruction efficiency.
And when you cover its construction, did you require at least 2 hits in the tracker or not?
For this one, at least 2 hits in the tracker, no more. You need to be within the second double layer and the innermost layer of the inner tracker. So you need 2 or 6 hits.
If you need 6 hits, you cannot have efficiency at 50 centimeters, right?
At 50 millimeters, what do you mean?
If you require to hit consecutive up to the 120 millimeter layer, then the efficiency would be very low. Is this the full construction efficiency or the hit efficiency for each layer?
No, this is the signal reconstruction efficiency. So
okay,
the signal.
Then if you tell me I have to hit the layer at the 120 millimeter, how come I have non-zero?
Oh yeah. No. I said it wrong. Sorry. What I meant to say, or what I should have said, is that you require at least to be within after the second double layer to here. So that means that could be four hits, because you get 2 hits from here and 2 hits from here. So at least 4 hits.
So what's your layer design? You assume there's one layer, double hit layer at 2.5.
Yeah, this one is double layer, and this one is also double layer, double layer, double layer. Yeah.
That's the assumption.
Yeah, exactly. This is a design from 3 years ago. There's new detector design. I'll mention it in a second. And this search, when you apply it for the triplet, the Wino-like state, at the 10 TeV muon collider, it covers a region of masses and lifetime that covers the thermal target. Okay? So the Wino has a nice lifetime that it falls in the acceptance, and it can be reconstructed very nicely, the Wino.
But again, sorry, but just to remind, the thermal target means 100% done.
For Wino, and this is compatible with our standard.
Yeah.
Different.
Yes, exactly. You see how the 100 TeV proton collider, the 10 TeV muon collider, they get all the way there to the thermal target. Yes, good. Then the Higgsino, it has a shorter lifetime, right? This is the doublet, again 10 TeV collider. So then the 5 sigma, which is the solid lines, they are very borderline to get the thermal target. So the situation is more or less like this. Both the SCCHH, the 10 TeV muon collider, they are right there.
Oh,
And then click does a good job. And then you ask the question, right? If the click is a lepton collider, does the job, why is that the 3 TeV muon collider doesn't, right? That's a very good question. Which is right here, right? It seems like we need the very last stage of the different projects in order to be able to find the Higgsino, right? That's what I mean here. Click 3 TeV is the last stage of click, the 10 TeV is the and so on. It's the last stage. But this is weird, right? 3 TeV here, 3 TeV here, and why not? Yeah. And it's because at 3 TeV, with the short lifetime of the Higgsino gets immersed in this beam-induced background dominated volume. So it doesn't really reach what you want, where you have good acceptance. That's the problem. So we decided to do something else. And now instead of looking at this, instead, you could look at the two, but we decided not to look at this at all. And just pay attention to the decay product of that particle. Yeah. Because the Higgsino at 3 TeV is very prompt. So this is going to be there isn't many disappearing tracks really. So it's mostly the soft track. Yeah. And because I'm running out of time, I should say very quickly that so you need to do this also model by model in the sense that for a given splitting, right? Let's say for the pure Higgsino case, the splitting is 0.3, as I told you before. That gives you an 90% of branching ratio to pions, and other 10% to light leptons. But then for us, these three objects are soft tracks. Okay. So what's the signal we're after? We're after a signal that for the PT of the soft track, it peaks at around 0.3, and then it falls very rapidly. So PT is below 0.75. So it's very, very soft. Yeah. And the number of events, the cross section for this cross section.
come on, you piece of shit.
At the 1.1 TeV, the thermal target, Higgsino, we're talking about 10 femtobars. And the luminosity is going to be 1 attobar. So at this moment, you would say about 10,000 events signal. Yeah. But then each chargino might give you, so it'll give you a soft track, but then that soft track might fall in out of your acceptance, right? So then really you need to explore different signal regions where you have one soft track, no photon, or 1 photon, and then 2 soft track, 0 photon, 1 photon. We did some study, some preliminary studies looking for these different signal regions. What's the good one? What's the best one to do signal background discrimination? We found this one to be the best, and only 9% of signal events fall there. So really, you're looking for what is 1,000 events in this soft PT region, right? So very challenging. And this is what you have to deal with. How good do we reconstruct tracks in the muon collider, given the beep? The beep ruins your ability to reconstruct tracks because you overwhelm the detector, right? And then the detector might not really identify your tracks. But then there's good reconstruction in the barrel. The really bad is towards the caps, right? So then you need to do this. Oh, and then here's something fortunate that happens, which is that the signal, this is soft track from the signal. They are very central. this neutral current cross section, it gives you very central events. And this is within, so 60 degrees polar angle and 90. You get most of the signal events right there. Whereas the beep, the background events, they are very forward, as I told you before. So that's good. We exploited that.
Explain to me again why the beeps are so forward. There's nothing in the central region, or there's still small amount.
Yeah, I mean, I'm normalizing this to
Yeah,
some,
it's
so
huge
it's,
number, right?
yeah, it's
So what's in the center? Can you zoom in the central region and tell me what's the distribution and number of events there? This one is deceiving. It seems like 0, but that's not.
but it's very, very, very small.
Yeah,
Look
so
at this.
what's the distribution? What's the number?
I don't have it here handy, but I can tell you, for example, that only that, so only beep overlay is what gives you this. So look at this efficiency. If you remember the stuff, the disappearing track, this is a smaller efficiency. It's harder.
This is a signal. I'm asking about background.
No, but to get this number, you have the beep overlay on it, because that reduces the ability to reconstruct your signal.
No, that's the beep impact on reduction of signal reconstruction.
Yes.
But that's not the beep efficiency. Beep itself, what's its number after reconstruction?
Okay, I owe you that, but I know within this 60 degrees is small. I mean, it's,
Okay, give me a reason why it's.
what I told you is the tracks are very forward, and we're asking for. Remember, we can get intuition here, right? So look at this. Look at this from electrons. Oh, yeah. So look at this. So this is falling before GV to very small levels. And our signal is 0.5, 0.7. So our signal is somewhere here.
Yes, I agree that a single beep event will not give you a hit in the transverse plane. If I have multiple hits, I connect them together. I will have.
Yeah.
Also, if I have the particle interact with the material, will generate pions. Those pions are soft pions as well, and they can their direction is random. Did you signal those pions?
Yeah. So
what's the number in them?
This is the full GM with the beep overlay, and
again, this is signal efficiency. That's not a background I'm asking.
but that's there. Like, let me tell you the final result, and I'll tell you everything that's there.
Well,
that's
I
in
know
there.
your final.
But this time the good efficiency volume is 60. Remember that before it was 40 for this disappearing track. Now it's 60. But then as opposed to the previous search, here's not only the beam induced background. Here you also have real processes that give you soft tracks, like any vector boson fusion process or some Baba-like process that emits a soft photon and the photon then splits.
Those are not my concern. What's the feedback? And to see the feedback. Those are standard model like WIMP processes.
Yeah. So what you want to know is this distribution all the way to 90.
Normalization, I have to see number, right? So we need this normalization is huge. You probably normalize to 10 to the 9 to the 10 per bunch process.
Yeah. I mean, I don't have it in a backup or anything, so I'll have to come back to you. Yeah. Okay. So then, so if you remember the signal is 1 femtobarns. It was 10, but only 10% in the signal region of interest. Look at those numbers. These numbers are very big compared to those. So you need to do something to discriminate now signal from background. And what you do is that you require an extra photon, the event, and then you start pushing the PT of that photon, right? Just to have an idea, without the photon, the number of soft tracks from only dital production, either vector boson fusion or Baba-like scattering. Look at the 9,000 signal events, but 10 to the 3 more background events. But at the moment you include this photon and you push the PT, now your tail needs to recoil, so the soft track stop being soft, and they fall out of the good acceptance, and now signal and background they start looking comparable. So you get this for the Higgsino. After including, so in here you also have the BIP tracks. So you have to do things like the angle between two tracks, you know the distribution from signal, you know the distribution from background, and you kill a lot of the background, both the real processing and BIP. Right, so this includes everything.
This includes every truthful particle, including the particle in the beam. Are there any fake tracks? Right? I can hit my layers with multiple beeps, okay? So each beep particle has low PD, I know that, but those hits, I don't know how to connect them. They're occupied, so I connect
Yes,
them.
and what I'm telling you is that doing this 40 GD here, this and an angle that I don't have the number now, but some angle between the two soft tracks, that beep, those beep tracks are below.
No, again,
They are gone.
Those are these truthful tracks of truthful PD of particles or include fake tracks? You include fake tracks.
We should come back to this because I ran out of time.
Fake track, you should have a clear answer of that.
We did include the tracks from the beep, the fake tracks from the beep.
Okay.
Yeah. So the beep affects you two ways. In one way, it spoils your probability of reconstructing your signal, but it also gives you fake tracks where the algorithm
So what's the fake track component? Do you have a number? You didn't list that in your background. If you go back to your slide.
Yes, what I'm telling you is that after these cuts, that number goes to zero. It doesn't even show up here.
After photon PD cut, it goes to zero. Is that what you're telling me?
After photon and distance between tracks, after all those cuts, it doesn't even show up here.
But before the photon cut, there should be some number.
There should be, and I owe you that number. I don't have the number. Yes, but yes, but yeah, believe me, this includes everything. Yeah. So you see now that this is more than 5 sigma. I mean, this is the Higgsino at the 3 TeV. So we said yes, not as good as Click, but you get to the thermal target at the 3 TeV collider. And this is the result from the full simulation, right? So just to summarize, this is what I'm telling you about the roadmap towards the minimal WIMPs is that the 3 TeV collider, so the LHC will do so much in covering this space. The 3 TeV collider could go and probe the doublet, the Higgsino case, all the way to the thermal target from the soft tracks. You do this appearance track, and then you could also probe the triplet that gives you 10% of that matter, 20% of that matter, and even 5-plet if it's just 1% of that matter. Maybe that's not highly motivating. But then at the 10 TeV collider, now you look at this appearance track, and then you can start reaching the triplet all the way to the thermal target. And then 5-plets, if they give you between 10 and 15% of that matter, they start showing up in these searches. And that's basically the punchline. That's basically what I mean by this road towards the minimal WIMPs. And thank you so much for it. Here I'm just saying that, so this is collaboration between theorists and experimentalists. I feel lucky of being part of that collaboration, you know. And I think so, at least when we started this 3-4 years ago, that was before P5. So if you say the words muon collider, people will look at you like, wait, do we understand the muon collider? So we really needed to do the texture simulation, all this to convince people that, you know, this is a good projection and all that. So,
so the 10 TeV muon collider gives you 100% access, 100% or doublet and triplet.
Doublet and triplets, yes. Yeah, but I guess one of my points is that already at the earliest stage, at the 3 TeV, you can already go and do the doublets. Yeah.
Yeah.
So.
That's out of curiosity, because I have some Japanese friends of mine. So U plus how much of the story will change? You said from some U plus.
Yeah, they are currently visiting Fermilab, and they asked me this question if we could do the simulation for the mu plus. And the problem is that, but problem or no, let's see. So Kitano, he just looked into this plot. So this is order 20 events. So, and remember, I had 1,000 to begin with. So it's a almost 2 orders of magnitude reduction, right? After all these cuts that clean up your signal. So you look at this plot between neutral current chi plus chi minus production and vector boson fusion. Sorry, this one. That's 2 orders of magnitude. And this is what they. Yeah, so they can only produce chi from vector boson fusion.
Yeah.
So then they are already at a very critical. But this is 3 TeV. They can do 10 TeV, and maybe they could do something. That's what I told him, and we'll see if we can do that or not.
So I think this second paper is major improvement. So you can say straight TeV actually can exclude or discover. Is it the exclusion limit or discovery limit?
This, as you can see, is more. This is more than 5 sigmas. This is discovery. Yeah.
Yeah. So before in our study we thought straight TeV without luminosity it's too hard to beat the image in the background. So I think so we need higher energy or higher luminosity to say something definitely about it.
Yeah. Yeah. And
can I go back one plot?
this one.
10 TeV, 10 TeV.
10 TeV, yes.
I recall in your first paper, in your simulation, your lifetime was wrong. I point out to you. Did you
Yes.
correct that? And
Yes,
is it the
yes.
corrected version?
Yeah. And if I'm not mistaken, we said that the Higgsino lifetime was bigger.
In your simulations, you have a round deficiency that I cannot agree.
Yes.
So this is a corrected.
Yes, is correct. Yes.
A little beat up.
Yeah. In that, when we did that wrong, the 10 TeV could get the Higgsino quite conclusively. We corrected that, and that's when we get that the 10 TeV barely gets the Higgsino. And then yes. And something that I can say is that there are recent, after P5, after all this, there's recent detector designs and recent BIM-induced background data. And there's a preliminary study by people in Chicago, experimentalists mostly, and then so they have found similar results, similar efficiencies, similar. So it seems like the numbers are solid even with new designs. It's good.
And in terms of Susie, 3 TeV, we know that's mini split. What's the prediction? Do you remember?
No.
So in those two benchmarks are essentially pure, right? You decouple the
No.
the spectrum. So it's I think it's closer to the mini split. You put the other particles heavy, right? So it doesn't affect the output. Calculated. If any 3 particles are closer, the mass gap need to be adjusted, but things you also have more observability, right? You have other particles to produce and to see.
Yeah.
So it's a similar line that is pure Wino and pure Higgsino cases are still the hardest case to do. As the sum of target is higher, because you don't have any other object to help you. It's easier to operate. Yeah. So that's a meaningful benchmark. That's why there are so many studies trying to say how early I can see.
Yeah.
They are working, pushing.
Yeah. It's good. No, but like I think so we're working on this actually quantifying these cartoons that you didn't like. Because as I told you, it needs to be model by model to be precise,
So
to be
you can tell
so
people
yeah.
It's this model, but you can remove axes and calculate. But there must be a calculation behind. Otherwise, you're just drawing random curves.
No, yeah. So we're doing the triplet right now because it's the easiest, and you get bounds from this side. So it's like the triplet seems to be the one that we could cover first. You combine all the fronts, And then the doublet's tricky.
WIMP is 20. If you-
Oh, yeah. The LXC can only do so much, the indirect detection do so much, but there is still room where only the 10 oh, I mean, not only, but the future colliders would cover. Yeah. Because the FCCHH could also do it.
Okay, great.
Good.
No further questions?
Thank you.
The speaker?
Yeah.
So, we will have organized a dinner. If you want to join, you can just react to the Slack channel or just let me know. We will tell you. There's some new blog I haven't seen. Can you go back?
At the end.
Yeah. The second paper. Okay. Within the IMCC, I reviewed it. So your update will respect to my
Yeah.
comments.
This is not public.
No. You go.
Bye.
This one, next one.
Like,
Yeah, this one.
Yes.
So those are all real particles, right?
Yes.
So where's the fake tracks? There's no fake tracks.
Mhm.
You claim you study that. Okay.
Yeah.
There's a chance for them to pair up with the photon, right? So I should know there's a non-zero possibility.
Yes. Yeah.
What's my non-zero possibility?
So what I'm telling you is that if we make the same plot without the photon,
Yes,
this would be.
I understand. It will be buried, but it's important to see what are the others.
But then what I'm saying is that so the 3 TV, so the beep, so like the signal would be like this. The other ones will be like 3 orders of magnitude above, and the beep line is somewhere. I don't know exactly where.
So beep did not dominate the background.
No. It could. I did not see this plot before the photon. So, but the what I'm telling you is that from here to delta R of soft tracks and the PT of the photon and some other cuts, that's when we get this plot. And so the beep tracks, they're just. So Federico also looked into it really the same thing. So imagine 2 soft tracks from a pair of towels. That's a lot. And then you pair that with random hits in the calorimeter that look like a photon. That could also happen. And
so photon events rate is actually high. You understand, right? The Baba scattering photon is always there. Okay. So you're basically asking for all my collision events with the photon inclusively, which is a high rate. What's the chance of that photon simultaneously happening because you have a time window with a beep background, induced background from 2 particles of fake tracks? That possibility is hard to estimate. But since you guys did the full simulation, I would we should be able to know that. Right?
Yeah, I see. But I'll ask Federico to provide a plot like this without the.
Let me see. I think I also when review your paper in IMCC, I also give some comments about backgrounds. I think you include more process.
Were you the one who mentioned about the Baba-like scattering?
Yeah, I think so.
Yes.
I was a reviewer. So.
Yeah. So yeah, this process here, that's the reason why. Wait.
There's also a few coincidental events that I mentioned.
Yeah, that's the reason why this number is larger than this number, like by a lot.
Yeah.
That's the Baba that you pointed out.
Yeah. Well, you know, I only spent time reading your first version. I didn't, you know, since you guys claim you addressed my thoughts, I didn't read it. Within the IMCC.
Yeah.
That's fine.
Yeah. So. Yeah, for the 10 TV, this is going to be a nightmare because the background is vector Boson fusion dominated. So the background increases at 10 TV, whereas the signal is S channel. The signal decreases. Yeah, like.
But there's important gain for 10 TV. That is, they have higher boosts that have high probability to see them. So that's why
So,
for my study, 10 TeV can discover it, already.
yeah. And something that Andrea pointed out is that 10 TV maybe
Like,
what you want to do is now to look for this and this.
Yeah, of course you can do that.
Uh-huh.
There are more proposals like that for other.
Yes.
So you can do that to impress, but even without that, without soft compiler, you can already make a good coverage. Of course, you can improve that. I have no doubt.
Yeah. Yeah.
But did this second paper got accepted by PRL or not?
It's being reviewed.
Oh, okay, there's no report yet.
No, we have, there's one referee report, but we're waiting for the second